Hi everyone, this is it. This is the last set of slides and we're done this course for this semester. I must confess it's been a hell of a ride. These last little few weeks have been quite the challenge. I think we'll get through it and everything will be great. So I'll get started. This is the last part. This physiology has to do with some things other than what's occurring sort of at the microscopic level with muscle tissue. These are other parts of a muscle contraction. With the first being length and tension. So there's something called the length-tension relationship. The actual definition of the length-tension relationship is a muscle fiber develops its greatest tension when there is an optimal zone of overlap between thick and thin filaments. Please remember that tension created by muscle is what we call strength. So it is the amount of tension that a muscle can create and what that tension can, shall we say, move, that is what we call strength. And it makes sense that if we have these cross bridges between actin and myosin that are occurring, for obvious reasons, the more connections there are between actin and myosin, in other words, the more overlap there is, then obviously the more tension that can be created. So when we look at this length-tension relationship, and we know that the greatest tension is when there is the optimal amount of overlap of actin and myosin, it is also influential by the length of the sarcomeres within a muscle before it begins. So we say that the forcefulness of muscle contraction depends on the length of the sarcomeres within a muscle before contraction begins. So I'll go on a little bit more about that, but we'll continue and then we'll go from there. So when we look at the sarcomeres, and we remember that sarcomeres line one up against the other, end to end in a muscle fiber, and that a muscle is made up of muscle fibers, then we can say, of course, whatever we're looking at in the perspective of the sarcomere also relates or correlates directly to the muscle itself. So if whatever we're talking about occurring at a sarcomere level is also correlating to the muscle itself. So we can say that the maximum muscle tension occurs when the zone of overlap between the filaments extends from the edge of the H zone to one end of a thick filament. In other words, it represents 1.2 times the muscle's normal resting length. So what is the resting length? That becomes the big question. We have to remember that, within a resting length, muscles don't, when they rest, just be their full length, right? If we go to the biceps, for example, if you literally look at your arm right now, just hang it off your side, would it be fair to say that there is a bit of flexion in that elbow? And you'll find that there is. And so we could say that, with this minor flexion at the elbow, that represents the resting length of the biceps muscle. Let's say we'll just isolate the biceps muscle. So that slight flexion in the elbow represents the resting length of the biceps. What I'm saying is that to achieve the greatest amount of tension in the muscle, it must be 1.2 times its normal resting length. In other words, to gain the best amount of tension in this muscle is to take that slightly flexed elbow of the biceps and lengthen it a little bit. Lengthen that elbow, extend that arm, lessen that flexion degree in the elbow, and now you're representing the better amount of tension created because now you've placed a bit of length on that resting length muscle. So a resting muscle still has existing tension at its two attachments, and we know that, right? That we call that tone, existing tone. And the fact that I just, showed you the example of the slight flexion in the elbow gives you the sense that there's still existing tension. And if we were to remove the muscle at its two attachments, it would shorten. And that's the one thing to realize, again, that, a resting muscle is not resting, like completely flaccid, relaxed. So if I were to take your bicep and tear, let's say you were doing something, and you tore off the distal attachment of biceps, that muscle would shorten considerably. It would roll up into a ball, getting up closer to the shoulder joint because of this tension that exists in it. So therefore, the amount of tension on the muscle increases the strength of contraction, and as I say here in brackets, to a point. If a muscle is stretched too far, the overlap of actin and myosin shortens and fewer myosin heads can attach. So in other words, if I take and I go beyond that 1.2 length, I have taken, remember this correlation between the muscle and the sarcomere, if I lengthen that muscle too far, the ability of actin and myosin to attach becomes extremely minimal because we have gotten the Z discs as far away as possible in that lengthened position. And only a small minor amount of overlap is occurring between actin and myosin. So therefore, if a muscle is stretched too far, the overlap of actin and myosin shortens and fewer myosin heads can attach. So therefore, tension decreases. At 170% of stretch, there is no overlap and therefore no tension and no contraction. So we can actually lengthen a muscle to the point where it cannot contract because the architectural design of the sarcomere would be such that there's absolutely no ability for overlap to occur between the actin and myosin. As we shorten the sarcomere away from that optimum, the tension decreases again. So we have an over lengthening of the sarcomere results in minimal tension. The same thing happens if we shorten a muscle too much. If we take a muscle and we shorten it too much, we also begin to decrease its ability to create tension. So if we're shortening a muscle too much, the thick filaments crumple as they're compressed by the Z discs. Again, we can't have good overlap connection between actin and myosin. So too long a muscle results in inability to cross bridge, or to a point if we get too long, no cross bridge occurs. If we shorten a muscle too much, we crumple the architectural design of the sarcomere, and again, we can't achieve good cross bridges. So too long a muscle or too short a muscle, we diminish its ability to create tension. Therefore, we can say that the existing tension in a resting muscle allows for the optimum tension created when contracting. So the reason then for this slightly shortened state, or this resting position, this allows for optimum creation of tension when a muscle is asked to perform a task. So we can see here then, when we talk about the length tension, what we're saying is that depending on the length of the muscle can result in either a lessening of tension or a ability to create optimum tension. So we can see here when we look at muscle tension and muscle length, in this side here on this graph, we can see that if this side represents short and this side represents length, if a muscle is too short, it can't produce much tension. If a muscle is too long, it also cannot produce enough tension. So there is an optimum length of muscle for maximum tension. In other words, at a particular length, we get the greatest amount of cross bridges between actin and myosin, and therefore the muscle can create a large amount of tension. So when we look on this side and we see here the same idea, when we look at the percentage of resting length here between 100 and 120, we can see that we can achieve the greatest amount of tension. In other words, at this length, there is maximum overlap of myofilaments producing maximum number of cross bridges, and therefore can create the maximum amount of tension. So in other words, let's go back to this side and let's just talk about a biceps curl. If I take my arm in a biceps curl and I completely lengthen my arm till it's as long as it can get, my biceps is as long as it can get anatomically because the olecranon is into the distal radius and it can only get so long. What we're saying is that whatever weight I place in my arm to do the bicep curl, as I start at the beginning, my perception is going to be of difficulty because I am only able to create a minor amount of tension. As I move my arm through the biceps curl, I will be able to feel as though the work is easier because as I go into flexion through the bicep curl, I am shortening the muscle and achieving the optimum length for maximum tension. So as my curl goes from fully straight into flexion at the elbow, the work becomes easier because I am creating maximum tension. As I continue and bring my hand up towards my shoulder, I am beginning to shorten the sarcomeres, and the end of the biceps curl will also seem difficult because I am not at the optimum length for cross bridges to create tension. So through an arm curl, the beginning and the end will be more difficult as compared to the middle because of this relationship of cross bridges when we look at the sarcomere and the length of the sarcomere and therefore the length of the muscle. We see it here again as it represents, excuse me, as it represents the length tension curve. We can see the relationship here of the actin and myosin. You can see here extremely shortened, creates minor amount of tension. And then as the relationship moves through between the two of them, we start to achieve optimum relationship between actin and myosin. And as they get further and further apart, we get to a point where, again, we can only achieve minor amounts of tension because they're too far apart. So where does this come into play? Well, first is obviously if I'm going to create a resistance program for a patient, I need to think about, where's their maximum in relationship to things. The second part is if I have a muscle that is extremely tight and possibly spasming, I can actually stretch that muscle out to a point where it can't spasm simply because the relationship between the actin and myosin can't create that contraction of spasm and the muscle will relax. When we look at a muscle contraction, it actually is represented by what is called a twitch. A twitch is a brief contraction of all the muscles in a motor unit in response to a single action potential in its motor neuron. So imagine a single action potential sent by the terminal end of the motor neuron crosses the synaptic cleft, and the acetylcholine attaches to the acetylcholine receptors on the sarcolemma, creates an action potential, moves along the sarcolemma, down the T-tubule. We get all the things that happen between the terminal cisternae and the actin and myosin and troponin tropomyosin complex, so on and so forth. That is a single twitch. This can be accomplished by an instantaneous electrical excitation of a nerve to a muscle or by passing a short electrical stimulus through the muscle itself. And this is what muscle stim does. So we can put two pads on a muscle and run a current through the muscle, thus causing an action potential, not by the nervous system, but actually by the electrical current of the device, and we can create a twitch. And a twitch can last anywhere between 20 to 200 milliseconds. So it's very, very quick. Now, when we have the stimulus and the beginning of a contraction, there is a minor delay that occurs. And this is known as the latent period. And this occurs as the action potential is spreading throughout the sarcolemma and the calcium ions are released from the tubules. So it does take a little bit of time for the message to cross the synaptic cleft, for the creation of the action potential, for the action potential to move along the sarcolemma, for the action potential to go down the T-tubule, stimulate the terminal cisternae to release the calcium. And this is known as the latent period, this minor amount of time where things occur. It is quick, but it is there. The calcium then, of course, as we know, binds to the troponin and exposing the myosin binding sites, and we get contraction. This is known as the contraction period. So we have the latent period as things are getting ready to go, and then we have the contraction period as we have the interaction between the actin and myosin and the conformational change of the troponin tropomyosin complex. Now we've had the contraction and we have to pump the calcium back into the terminal cisternae and the tubules of the sarcoplasmic reticulum. So we are, because if we don't, they'll stay connected in a state of what's called rigor. So we have to pump all the calcium back out to make an environment of less calcium around the actin and myosin molecules. So as the calcium is then actively pumped back into the tubules, the binding sites are recovered. So the tropomyosin troponin complex covers back over those binding sites, and the actin and myosin relax. This is known as the relaxation period. So we have the latent period, which has the action potential working its way through in the release of calcium. We have the contraction period, which represents the interaction and cross bridges between the actin and myosin molecules. And then as calcium is pumped back out of that sarcoplasm area and going back into the sarcoplasmic reticulum, we have the relaxation period. If another stimulation is applied immediately after the first, the muscle will respond to the first but not to the second, because it has to go through this step every time for a muscle contraction to occur. So as the calcium is being pumped back into the terminal cisternae, if another stimulus comes in at that point, we will not get a contraction because we're not set up for another one. So what's important within this single muscle twitch is when a muscle fiber receives enough stimulation to contract, it temporarily loses its excitability and cannot respond to another stimulus. And this is known as the refractory period. You are going to learn a technique in massage for relaxing muscles where you actually make the muscle contract. So you actually contract the muscle, and then you're playing around with this. You're contracting the muscle, and then immediately afterwards you're stretching it because you're actually allowing that muscle to lengthen because it is in a refractory period. This is slightly different than PNF. This uses a different modality in order to stretch a muscle or to lengthen a muscle, but just the same, if you contract a muscle immediately after, you can lengthen it to some degree because it's in the refractory period. So I've talked a little bit about this. I just want to go over it just again, just to remember, as we've stated, a twitch is a single muscle fiber reaction to a single stimulus. And the thing to remember is when we get a full contraction, when we're doing the work, it is the culmination of twitches that results in the full contraction that you see when you're performing a task, such as doing a biceps curl with a dumbbell. So as was stated above, a twitch is a single muscle fiber reaction to a single stimulus. The speed in which a muscle contracts usually reflects the type of function it performs. As an example, a fast twitch muscle is an ocular muscle such as the eye, where rapid eye movements are required. Whereas a slow twitch muscle we find in the distal leg, part of the calf muscle, is known as the soleus, because it's concerned with weight bearing and postural changes. So it doesn't need to make quick changes, nor do we want it to, because it's firing along to keep us standing properly and so forth. So the speed at which the stimulus travels, it depends on whether the muscle is a slow twitch or fast twitch, and that a single twitch causes contraction. So I said that we have to have a number of twitches in order to have a contraction, and this is known as summation. Summation means the adding together of individual twitches to make strong and concerted muscle movements. So although I discussed a twitch, it is the culmination of a number of twitches working one after the other, so adding together individual muscle twitches to make a strong and concerted muscle movement. How does this occur? It can occur one of two ways. Increasing the number of motor units contracting simultaneously. Because remember, a motor neuron, right, branches out and innervates every single muscle fiber in that muscle. So when we talk about recruitment, we're talking about how many of those muscle fibers are stimulated. 1%, 2%, 10%, 100%. The other way that we can have a concerted strong muscle contraction is increasing the rapidity of contraction of individual motor units. So we have a twitch, and the faster those twitches happen, the more contraction we get. Yes, I said there was a refractory period where we can't have a contraction, but we're talking very, very quick timings in between. So we can get a twitch that gets faster and faster, and then we get a full contraction. If I had a muscle stimulator, I could show you. I could actually put the pads on an arm and slowly turn it up, and you would see the twitch of muscle. And as I turn that muscle stim up, I would start speeding up those twitches so quickly that the muscle that I was stimulating would go into a full and complete contraction. In fact, it's one of those things you have to be careful of with a muscle stim. If you turn them up enough, I can actually make a muscle contract so significantly, it's conceivable that I could actually tear it off of one of the attachment points because I'd make it contract so strongly. So basically, these are the two areas. So I can recruit more motor units contracting simultaneously. I also increase the rapidity of the twitch. So when a muscle is stimulated then at progressively greater frequencies, its degree of contraction becomes progressively greater. As I said, the faster and more we have, the more it becomes. This is known as frequency summation. So I'm increasing the number of twitches, and they sum together to create enough stimulus for a contraction. As the frequencies become greater, they eventually reach a point where they cannot be distinguished one from another. That's when we get the contraction. If we continue speeding up the twitches, they eventually reach a point where the frequency fuses and the muscle ends up in a constant state of contraction. And when we have this constant state of contraction, you might know it as maybe a Charlie horse as an example, where the muscles just bang, it's just in contraction and it's not relaxing. This is known as Teton Ization or tetany. So what's happened is the frequency of the twitches, as I said, initially starts as a twitch. It gets fast enough to have a contraction. If it continues to come faster, you end up in a constant static state of contraction. This is known as Teton Ization or tetany. As a note, tetany also means that the myofibrils are constantly bathed in calcium, which allows the active binding sites to stay exposed. So this is what happens. And again, if you don't have that pumping out of calcium back into the terminal cisternae in the tubules, you would end up in a tetany state because there's constant calcium there. The troponin tropomyosin complex is pulled out of the way, and the actin-myosin cross bridges just get stuck there, and you stay in a constant state of contraction. Just to let you know about something called rigor mortis. So when someone dies, rigor mortis is a state where muscles go into what would be a hardened, shortened state. The reason for this is because the individual has passed away, the calcium pumps to pump calcium back into the terminal cisternae and tubules is gone. It doesn't work anymore. We're not creating ATP any longer. There are minor amounts around. It's the reason why we go into and out of rigor mortis. But this is the reason why we go into a state of rigor when we die, is because their calcium doesn't get pumped out. It just kind of hangs around in the sarcomere, and these actin-myosin molecules stay connected. I sort of alluded to this is using more and more motor units. And so multiple motor unit summation is about motor unit recruitment. And I think I've alluded to this in the past. The amount of work a muscle needs to do is, when we think about that all or none principle, a single fiber when stimulated contracts to its utmost. When we are looking at whether we lift a 5-pound weight or a 20-pound weight, this is about motor unit summation or recruitment. So that the brain determines, in looking at it and possibly previous history of lifting and so forth, it has a sense or an idea of how much motor unit recruitment is required to perform the task. Normally, the different motor units are not stimulated to contract in unison. Some motor units will be active while others will be inactive. And the reason for that is, in the inactive state, it can recover. So if we're asking a motor to perform a task, there's always movement between motor unit recruitment. So as a fiber recruits, or is recruited and contracts, it needs time to go back into that refractory period and relax to work again. So this is why we have motor units being stimulated and not at any given time when we do work. So some motor units will be active while others will be inactive or relaxed state. And the purpose for this is to avoid muscle fatigue. The weakest are utilized first, while others are progressively utilized if the muscle is required to perform a greater contraction. This also allows for smoother movements. And as well to remember is, I can reach a point where I can apply a resistance to a muscle, and even with massive or maximum amount of motor unit recruitment, you can't shorten that muscle because all those do not have the ability to create enough tension to move whatever weight or resistance I've placed on it. Okay, gang, that's it. We're done. This course is over. It's been a hell of a ride, as I've said in the past, and we'll see you next week. I'm sure you'll have some questions in regard to this material. This will be, I'm hoping, on the next quiz. I'm going to send an announcement out for next week for the next quiz, and then we'll have our final the week after. Again, thanks for listening. Thanks for all your patience in terms of what's going on in the world right now, and we'll see you next week.